I could ask everyone to please put their phone or headset on mute. And I believe if you have if you're calling in on the IP headset, there is a little microphone on the far hand side. If you just press that so it turns red, then that will put you on mute. It helps with the background noise, or if you have a little bit weaker connection, then the static ends up affecting all of us. And similarly, if you're on a landline, I believe the number is *6 or #6. I can't remember which way to go back and forth. Thank you. And then also, if you have questions as we go along, we'll try to keep track of them in the chat, but we do have a Q&A at the end. And if there are questions in the chat that we do not answer or get to answer in the time of the seminar, we will take track of all those and attach them as an accompanying file to the presentation, which will be posted. And this session is also being recorded. So once again, welcome. I'm Ian Verhappen, and just a little bit about who I am and what kind of trouble I've been in since I started my career about 30 years ago. I'm a professional engineer, a CAP. I spent about 20 years in the oil sands, and I worked for a division of Cooper Krause Hines for about 3 years as an employee, an additional 2 years as a contractor. Been very active in ISA standards and practices and IEC practices for quite a number of years. And probably a few of you know that what I did get my ISA fellow for was my activities in the area of industrial networks and communications. So I will now hand you over to my co-presenter, Brian, who will tell you a bit about himself and get us started.
Yeah, thanks, Ian. I'm with Cooper Busman's Wireless Business Unit. I work as an applications engineer here. And prior to that, the company was called Omnex Control Systems. Cooper purchased Omnex, I think it was about four or 5 years ago now, or something like that. And Omnex was a wireless company in the industrial field, making radio systems that communicate machine to machine. So typically programmable logic controllers to DCSs to field 4 to 20 milliamp sensors. And I've been with them in a variety of different roles for 13 years now, and 21 years ago was when I finished my schooling, and I went through the electrical engineering program at BCIT, and process automation and instrumentation was the option that I took that by far I thought was going to be the far more interesting of them, and it's proven to be so. Currently, training support role. And I think it's the most interesting aspect. After years of development of a product, and then the sales team takes it to the market, and the customers make their decisions to buy the products, I'm the guy who makes it do what it's supposed to do. So I think it's by far a very, very interesting role here. So today we've got a number of different subjects that we're going to talk about. Focused around network management, of course. First of all, why it is now becoming a critical aspect to monitor. Similar to temperatures and pressures and this sort of thing, customers want to know, how reliable are my communications? We're going to chat about what we did in the past and what sort of tools were available. And then we're going to talk about the trade-offs there, or what it cost users not to have this information, and of course how they dealt with it. What did they do? Then we're going to chat about the new diagnostic tools that are available, and what benefits the new tools provide, and how that impacts reliability and operations of industrial facilities. And then lastly, what's the bottom line at the end of the day? What's the return on investment with a network management system? So with that, I'm going to turn it over to Ian, and I'll just bring it on. We're going to start chatting about why a network management system here. Okay, Ian, you have the floor, so to speak. Oh, geez, I think I jumped ahead one slide too early. Oh, thanks, Ian. It looks like I'm back here. Sorry, I passed it off to Ian one a little bit too early. One of the first things to think about is why do we have a network management system, or what's important about it? Well, it has to do a lot with just the increasing complexity of networks that are out there. People often start out with a handful of devices, just getting familiar with them and making sure they work properly and do what's advertised. And then as they begin to see value, they expand it, and sometimes they expand it quite dramatically. And now we can have networks that have hundreds, if not thousands, of remote sites. And my focus here is primarily going to be on the wireless communications. That's what Cooper Busman specializes in wireless products and equipment. And what that entails is distances. And these days, with a fixed frequency, 5-watt radio in the 450 megahertz band, we can achieve radio links of up to 50 miles. So you can imagine, from my perspective, telling a customer that, well, you have to drive out to that remote site to plug into that remote device to gather a couple of diagnostic tools before we can go further and figure out exactly where the problem is. And if once we report back with that information, it's possible we might have to go to some other remote sites. So the driving time, frankly, can be a big driver for people to want to monitor radio links. Then we have the automatic versus human effort. A lot of remote sites that I've dealt with or chatted to customers about, they don't do any monitoring of the quality of the signal. They just know that it's working, and frankly, that's the most important thing. So often it's just responding to problems when they occur. So automating this effort, knowing how things are performing, and allowing you to predict when you might have a problem, therefore to be able to prevent it. I mean, preventative maintenance is certainly an extremely valuable aspect. It just cuts downtime, and we're going to chat about it at the very end as well when we talk about the return on the investment. So we also have some increased complexity, and particularly with mesh networking systems, whereby the mesh will automatically figure out which is the best path or what route it should take to get data from point A to point B. We might not no longer know exactly which radios are linking to one another. So it certainly makes it a lot tougher to be able to figure out where to go to troubleshoot these radio systems. So being able to monitor the network is certainly a key aspect of reliability and consistency of a product being produced. And here we go. Now we're ready to hand things over to Ian. And there we go. Ian, you have the floor.
Okay, thanks, Brian. Well, it all starts, as we know, with control folks about trying to figure out what we need what do we need from the network? What are the deliverables? So engineers tend to have a lot of wants. I know when I worked for MTL, when we were trying to develop new products, the engineers certainly were, well, that would be really cool to add, and I think all of us are familiar with bloatware. Here we developed this presentation in PowerPoint, and we have how many different features, and all of us, how many of them actually do we even know about or how to use? So a lot of those are wants. They're kind of nice to have. Someone, a power user, might use them. But in order to do what we actually have to do, that's the need, right? What is the core thing we're trying to accomplish? So In order to do that, some of the questions you ask are, what's the data speed and response time? Obviously, in process control, it's the response time that's critical. So what do we mean by real time? Real time is different things to different folks, as we'll show you in the next slide. What's the distance? What's the environment? What's happening between the nodes? Is it the nice bald prairies? Is it the mountains here, between Brian and I and so here in Alberta and BC, or is it water? All these things make a big difference. What are the temperatures? All this kind of stuff. So, the impact there would be, do we need repeaters, or can we just do it with a single line of sight? And then, of course, these things are distributed kind of everywhere. So what about power? All of us, of course, are concerned about cost. Licensing, that can be, usually licensing is not a challenge. You can usually find bandwidth. It's just a matter of going through the whole process of getting a licensed system. And then as we're moving more and more to sort of commercial off-the-shelf technologies, what type of security do you need, right? Or what added security? And then what type of data are we sending? Are we just sending all the data in, say, Modbus, simple protocol, Modbus, RTU, or are we combining? We have, in addition to Modbus, we might have a Profibus or DeviceNet or something like that. And do we need to change it? So is a gateway involved? Because really, what a gateway does is change protocols. So having a look at what's the definition of real time. And I guess what we're saying here is it depends who you're talking to. For meteorologists and so forth, we're talking about hours and what was the weather this hour or next hour, that type of thing. Mind you, as we saw with Sandy, some of those things were changing minute by minute, but generally the time frame is hours. Process control, we're kind of looking, depending on the flow loop, but in certainly the process industries, it tends to be in the order of seconds. On a crane, which is where Omnex sort of started some of their work, they're looking at fractions of a second. And then in machine control, you're looking at, like a 3-axis controller or something like that on an assembly line. You might be looking at milliseconds or nanoseconds. So real time is kind of relative, and so it again, that will have an impact on your network and what the expectations of that network are. So again, comes back to what are your needs and your wants. So what do you need for response time? And then secondly, what is the distance, right? How far is far enough? If you're doing environmental monitoring type of things, where you're doing pollution monitoring stations or that type of thing, or maybe a distributed gas field, as Brian alluded to, you can be talking in the order of hundreds of, 100 kilometers type of distance. 50 miles is roughly 80 kilometers. On SCADA systems for a water, pump stations across the city, like, so I live here in Calgary, and, the distance between the pump stations or the storm surge levels and stuff, you're looking in tens of kilometers. A typical process plant, you're looking at approximately a kilometer type of distance. Automation networks, like these mesh networks, field sensor networks that Brian alluded to already, you're looking at approximately 100 meters. And then IT networking is typically in the order of tens of meters, right, within a building type of thing. So from where you are to where the closest access point is typically distant. So again, we've covered two things: is how fast do we have to be, and how far do we have to go. Then, as we alluded to, how do I get power, right? Obviously, one of the big things we do for radio is we try to minimize the amount of power the radio itself needs, and so then we can operate longer if we need to on battery, or at least we only need a low power source there, right? A low load, a small load. So we can then perhaps power it with an environmental source, solar or wind or certainly here in Alberta in the natural gas industry, a lot of times we'll use combustion. So we'll make a thermal pile where we just burn a slipstream of the natural gas that we're gathering. However, some of those, of course, solar and wind not being there 100% of the time, certainly up here in the north in the winter, or it gets covered with snow, those types of things, then you have to have the battery, and you got to size that and so forth. And as we all know, automation systems tend to be in the 24-volt area. And so the challenge, of course, is getting that reliable power. As we know, these are always widely distributed, and so then the question becomes, well, how do I make sure that I get 24 volts when I need it, where I need it, all the time? And what we do for the smaller systems, like the process sensors, like our wireless transmitters, is batteries or some form of energy harvesting. And because this is so important to the reliability of systems, the ISA 100 committee ISA 100 has a working group on defining that interface to the energy supply, whether it's a battery or energy harvesting device of some sort, so that there's a standard way to connect them to the power supply. So when we're building a system, right, we have to match the hardware to the problem. So we've identified some of the things we think about when we're identifying the problem. So one thing is bandwidth, right? That's basically traffic. How much information are we going? If we're sending data only, as we know, that's a very small bandwidth. I'm sure all of us look at the data plans on our cell phone. And so if you look at a text message, right, that's not very much space. Or even if you look at say a Word document or something on your computer, if it's only text, you can get 10 pages of text for less than 100 KB, but as soon as you stick one image in there, now you've got a megabyte file. So that's just a picture, right? Now, what about streaming video? Okay, if you start putting streaming video in, well, there you go again. Right now you're talking about 30 pictures a second, so the bandwidth goes up exponentially. Distance. We talked about the distances that are possible with wireless, but typically for long distances we'll use fiber, and then for distances of within a building like 100 meters or so, we look at copper, the Cat5e cable, for example, or twisted pair going out to the field, right, where we're looking at could be hundreds of meters of cable. Then, because as we said, we're going to commercial off-the-shelf technology, we have to look at security. How do we keep the data going from the right people to the right people and making sure that what was sent actually gets received, right? The AAA, not the AAA Automobile Club, but the AAA for security. Authentication, authority, and I always forget the third one, but there's the AAA there. And then, so we have firewalls for that, and then switches and routers to manage the traffic, right? Making sure it gets from place to place. And lastly, we have to also look at the environment. I alluded to the weather already here in Canada, which is near and dear to Brian and I, of course. Whereas if you go down to the Gulf Coast, of course, we're more worried about the heat and humidity, and if you go certainly to places like Iran, Saudi Arabia, and the Middle East, then it's pretty much all heat. Okay, and then what about the area classification? So general purpose or Class 1 Division 2, right, or Zone 2, where it would be a potentially explosive atmosphere for a certain percentage of the time. So all these things need to be taken into consideration when we're building an industrial wireless system. And of course, when it's the beginning, the design, as we'll show you later, is where it all starts. But the reason it's so important to get your infrastructure right is that in order to get your AI, right, your analog input, in this case we're looking at a DP flow cell, up to our DCS, where we can do our PID or closed loop control, and then drive our valve or an analog output, we do need to have the wires, right? That's how the signals get from A to B. So now if we put if we took that out, right? If we took out our signal, right? Then we'd really, how would we wouldn't be getting the, right? We cut out the wire, we wouldn't get that signal either to go to the PID. So now what are you controlling to? How do you compare your set point, right? So everyone kind of takes it for granted that my signal is always going to get from A to B, uncorrupted, 100% accurate of the representative of the process. But what happens if that's not the case? And that's really what we're going to talk to you about today, is why we need to keep that physical layer so important, right? If that physical layer fails and you can't predict it, or you don't understand the consequences, you will certainly lose production, or depending on the signal itself, you could cause an entire plant outage. Okay, so we're showing the weakest link here in the chain is often the one you don't see right under the surface. So in order to do that, we need to identify the problem before the process is impacted. And if we do have a problem, we want to get that thing solved and back and up and running as quickly as we can. And so Brian talked about already how, if that means you have to drive out for 50 miles, then how long, that's a couple hours there. And assuming that he has cell coverage and can phone back and tell you what the problem is, then, maybe you can start troubleshooting it. Or you might identify that, oh no, now we have to go to the next station, another 50 miles, but to get that distance, you have to actually drive 75 or 80. You can see how the time will quickly add up. So as we all know, prevention is the cure. So we're going to talk about some of the tools here that can help us prevent things from happening. We talked about the physical layer being the cornerstone of the network. Well, if you look here at the OSI, or Open System Interconnect model, the physical layer is again the base on which all the other pieces of a protocol are based. Okay, so we have the physical layer, then the data link layer, which is typically Ethernet, right? What we think about. When most people think of Ethernet, though, they tend to think of layer 4 and below, but in reality, it's only layer 2. And then we end up at the very top of the OSI model with the different protocols. The reason the OSI model is so important is that you can use multiple different layers of protocol on the similar physical layer. So practically all the different bus protocols, Modbus, for example, is the one we've picked as an example. So you have Modbus. So you can get Modbus RTU, which is basically the serial version of Modbus. But by defining the different interfaces between the different layers of the OSI model, now you can use Modbus, which resides up here. And by changing the interfaces, you get Modbus TCP, which means now you have Modbus going over Ethernet. Okay? But the core is the physical layer. And as you can see, on the physical layer, if we look, we have the copper, fiber, and wireless. So the three options that we, typically people think of copper, for the long distance, the fiber. But now, more and more, as we're seeing both applied in the field and in our office environments, we are starting to use wireless more and more frequently. So that's what we're going to focus on today. So, where we got to today relies on our past. So what have we done in the past as far as process control and measurement? Well, for one thing, we're seeing more and more Ethernet, and that's, just the last, 15 years or so, we're really starting to see Ethernet. And I've always told all my friends that there's job security in acronyms. So here's a half a page of acronyms, and we'll cover a number of these today. But really, what these are is, shorthand. And I always say that the reason I say job security in acronyms is now we can talk about these terms. Others that don't know the language, they start getting the glazed look in their eyes, and then the engineers in this start doing the, yes, we've got another, right? We fooled another one. So they reaffirmed our stereotype, I suppose. But the core message is this there at the bottom of the slide. There are tons of different protocols out there, and they're just different ways, right? Remember, all we're trying to do is we're trying to connect or get a message in an understandable method from A to B, right? So we want to get from one transmitter up to a control system, or one transmitter out to a control valve, and how we get there is using these. These are just tools to help us get the message from one end to the other, okay? The one protocol that is very widely used for managing networks, or gathering the statistics and sharing the statistics of how well a network is operating, is SNMP, Simple Network Management Protocol. And it's part of the Internet Suite, so it's defined and managed by the Internet Engineering Task Force. So if you're interested, you can go to the IETF website and download the standard telling you how it works and how the database to share the different types of information and what their definitions are can be downloaded. But really what it does is it allows you to transfer information in a common format of how, different key parameters on the health of your network, okay? And I guess settings as well. All of us, I think, are probably familiar with ping. Basically, a ping is a certain type of IP utility where you send a message out to a specific address, and then you await the response. Okay, so it sends please send it. It's like sending a registered mail almost. You send a message out to someone, and then you get a confirmation that it comes back. And that just basically demonstrates that the two of them are connected, and so that eliminates at least some of the potential causes for lack of communication. Another tool is ARP, Address Resolution Protocol, and basically it's a tool that finds the address when only an IP address is known. So if you know the IP address, it can effectively go and get the hardware address, which is what you really is the identifies. The IP address can change with time, but the hardware address is fixed. It's like the MAC address in your computer, okay, on your Ethernet chip. NetStat, another abbreviation, is network statistics. It's just a tool that shows different connections between different devices and how the routing tables as well. So every device on a network has a table that correlates the IP address with the physical device, so you know who's connected to who and how. So it helps also determine the amount of traffic on a network and is available for Unix and Windows environment. The NetBIOS version of NetStat is NBTstat, and then the another useful file is called hosts, and basically what that does is it resolves the name between an IP address. So because not all engineers are uber geeks, but want to have a way that it's, just like we use tag numbers for our instruments in the field, well, we also give names to each of the nodes on a network. And so hosts file will record those names. So it might say that, Brian, so we'll name something Brian, and Brian might sit at IP address 255, 254, 250, 168, for example, okay? And so the host file would make that relationship or maintain that relationship for you. And then we have the Windows and the non-Windows version of ipconfig, which is basically to configure the IP system or the Internet protocol addresses. It will set up the subnet, and basically what it does is a subnet just breaks the whole domain into smaller, more manageable pieces, and also if you break them down into smaller pieces, it allows you to make more efficient use of the limited number of, well, certainly with IP version 4, the limited number of addresses that anyone would have. And basically what it does is it also works with another protocol called DHCP, which really automatically assigns IP addresses or maintains the IP address list. And sometimes, I mean, some of you, if you have a modem from, like I have a cable modem or I have a DSL modem, they have a very small address range. And so every so often, the first time you phone those folks and they say, hey, what's the problem? They tell you to reboot your modem, and what you're really doing is clearing the buffer because DHCP didn't do a very good job of releasing the least IP addresses. Then we have some routing. So you want to see how a message got from A to B. So it shows all the connections in between two different endpoints. Okay, and so traceroute does it automatically, and route allows you to manually say, I want to go from. So if I want to get from Brian, I want to go from. So I'm here in Calgary. So I don't know how many. So I'll go from my house. I'll go to my IP provider. My IP provider will go to his or to their equivalent office in Vancouver, and then from that office they'll go to whatever the IP provider is for Brian, and then that's how it will get to Brian. Okay, that would be an ideal world. Obviously, between Calgary and Vancouver, there's probably 2 or 3 hops as well. But you can actually, if you're internally and you manage all those yourself in your own network, you can manage those, set those up yourself with a preferred method of connecting A to B. So that's all the tools for traditional Ethernet, the IT type tools that transfer over to the Ethernet in the control domain. But we also have at the field level, right, traditional control signals. We have current and voltage, and HART is a superimposed digital signal over an analog current, but really we do use the current, right, as the PV. And so on the left we just show a calibration tool that generates 4 to 20 milliamps in different ways to calibrate your loop. On the right is a ground loop detector. You just clamp those big orange things around your wire or bundle of wires, and it will detect if there's a ground loop in one or more of the cables. And it's really important and a lot of times we found that when there is a problem in a system, it is typically in a ground loop is the first place to start looking anyway for a solution. So, we mentioned HART just now, and it's got some digital communications capability. So what's happening though is as we all know, there's more and more data coming because more and more, let's call them smart or intelligent devices coming at us more ways, and so that means more challenges. Okay, so what happens as a result of all this? Well, we look at the field level, right? We have the different field buses. I believe there's close to 30 different field buses now with the IEC. And a field bus is bidirectional communication of, still trying to do the PV, plus diagnostic data. And so even a relatively simple smart transmitter these days is capable of putting out sort of 300 plus data points on a per second basis. So, a lot of data to go back and forth. Field buses, because they're bidirectional, does allow remote configuration, and the problem or the challenge with going from an analog system to field bus is some of the infrastructure, at least some of the infrastructure, must be different. Obviously, some buses are designed that you can reuse the cable, but the communications card at either end have to be protocol specific, okay? But the next level is wireless, which is really field bus, the bidirectional capabilities of field bus without wires. However, most control systems do not have a wireless antenna on them, so they often need a gateway to convert from wireless to copper or wireless to fiber. Typically, it's wireless to copper. And then wireless needs that infrastructure. So just like we have with our traditional analog systems, we got our multi-pair conductors running out to the field, our copper wire going to the field. Well, with wireless, we need our multi-pair equivalent coming back to our control system, right? To our so from the equivalent of the junction box, right, back to the control system. So but once that infrastructure is in place, the beauty of wireless is that once the infrastructure is there, adding another node, another field node, is just simply a matter of basically purchasing and configuring the device, because if you design your system properly, that backhaul is going to have multiples of the bandwidth of what's coming from the field sensors. Okay, so since we need to have that reliability, right? Control systems are all about reliability. What can affect that reliability? What makes radio unreliable? Well, too many messages, not enough bandwidth. That's what I just alluded to, right? So you often will have your backhaul being multiples faster than your end nodes. If you don't have enough bandwidth, the first thing you're going to see is collisions. Okay, certainly with Ethernet, because that uses CSMA, right? Collision sensing multiple access. And you'll start, one of the other things that could be a cause of too many messages is you've got your update set too high, or not enough on a process transmitter. One of the important settings when you're doing a wireless transmitter is how much bandwidth or deadband you're going to set before you actually say the process has changed. Okay, so that's what we mean by sensitivity being too high. Okay, too small a fade margin. That's basically the amplitude or the intensity of your signal. And so if it's if it's not strong enough, just the slightest bit of interference, ice fog can mess things up. You get a weak signal with the wrong antenna gain or interference from nearby antennas. Again, earthing, right? You get a bad earth or ground, then you're going to get additional. Your signal will go the wrong way, right? Weak signal. Water is always a great conductor, but not conducting the right way. Damage to the insulating qualities of your antenna, okay, or a poor connector. Your mounting, right, is not. So you think you're basically you haven't tuned or focused your antenna to where it needs to be, and maybe there's a new obstruction. That's actually the one that's most common. You'll find that something moved, right? Certainly in a process environment, they might be doing some construction and they moved a crane, or they moved even just a truck for a while. And Brian will give some more examples in his later on in the presentation of the types of obstructions that you can't really plan for. So now we're looking at wireless, and you're saying, well, what options do I have? What choices do I have? As we said earlier, you can get a licensed radio. It does require that you apply for it and so forth. Typically, you will be able to get one. I know that a lot of times your supplier, such as the Cooper folks, will help you with that process if you choose to go that route. But more typically, and part of the reason for doing that is, of course, the economy of scale, we are doing more and more license-free or ISM, industry scientific medical bands, being used. And the most common one is the 2.4 gigahertz, right? that's the one that our phones work on. That's the one that our Wi-Fi works on, etc. Prior to that, though, there was quite a bit, at least in the industrial area, of 900 megahertz. But if you notice, you can see the next two entries here. These two entries here, there is a difference in what the definition of 900 megahertz is, depending on where you reside in the world. So that was a bit of a thing. You know, if you order a 900 megahertz radio, make sure that you know where it's going to end up being installed. Otherwise, you'll be contravening the ISM requirements. And then, as Brian said, for the longer distances, you can get the 400 megahertz type of radios. So if you have an ideal world, that would be this column called direct path. And so you can see that, 2.4 gigahertz, if you were shooting across the bald prairie with nothing in between, you could potentially obtain a kilometer distance. Obviously, you wouldn't get the full 100 megabits at that distance, but you could, distance and throughput are almost inverse. In an industrial plant, we're typically looking at lower data rates because we're not streaming anything. We are sending data predominantly. And just to be safe, you're looking at 50 meters, maybe 100 meters as the distance that you would use. Now, 2.4 gigahertz, we have different technologies. We have 802.11, which is Wi-Fi, which is basically wireless Ethernet. It uses multiple 11 megahertz channels, but typically we only use 3 of those channels to avoid overlap, okay? And we have power of, 30 to 300 milliwatts coming from the radio. The more common one that's used for the field sensor networks uses an 802.15 radio. So again, it's made to be compatible with 802.11. So there's some things built into it so that these two don't fight. And you'll notice that 802.15 is a 5 megahertz channel, so it's a smaller channel. And so if you pick the right channels in 802.15, you can almost avoid the ones that are most commonly used in 802.11 and thus get better reliability. 802.15 was designed for very low power, which is what we want, right, if we're having a battery-operated field device. And so typically it runs at a maximum of 10 milliwatts, right? So now we're looking at, even at the lowest, 3 times less than the lowest for an 802.11 radio. And where the heck, look at all the different options that you have, depending on the application, for the types of radio. So we have the 15.4, which is typically field sensors. We have Wi-Fi as one option for the backhaul, right, where we have that higher bandwidth. And then we also have WiMAX. WiMAX is 802.16, and that protocol is wide area networks, so that would get even longer distances. Properly deployed, WiMAX can cover kind of, let's say, portions or the greater portion of as much as a city, and it was originally intended to be a competitor to like a cable modem coming back to your house. So different levels and different bandwidths of the availability. So there's the field level, going back to the field level networks, right? We have different supplier solutions that are proprietary, shown here. Cooper Busman, for a number of years, they're probably one of the longer serving wireless networks, and they have a network called WIB that also uses 802.11 and they also support Fieldbus, Modbus, and Profibus protocols on that. And then we'll have, various from other manufacturers have proprietary protocols. And then we have the open IEC standards that we're Wireless HART, which is an IEC standard, approved IEC standard, and ISA 100, which is just out for ballot and should be approved very, very early next year. But both of these protocols have been approved by ANSI, do have the supporting infrastructure and necessary compliance institutes to confirm the they fit with their standards. So if we look at a plant where we're just looking at a single layer solution, okay, so now we're running everything on the same protocol, the same level. So let's assume, for example, that we're going to use here just all 802.11. So we start out, we're saying, perfect, let's give her a go. And then these are the first networks we install. Oh, now we get another one. And we start adding and building our system. And you can see that as we get the overlap, we're starting to run the risk of interference through the overlap. So we continue to build. And before we know it, you've got a hodgepodge and you run the risk of, how the heck am I going to manage this? Well, the simplest thing to do is to make a two-layer network, okay? So you have a sensor mesh or field sensor network, and then you have the backbone coming back. And what you can do is, to minimize the chances of interference, you can make these at either the same, so you can make them all 2.4 gigahertz, but pick different channels. Or you could make one 2.4 gigahertz, the other 900, or you could make one 2.4 gigahertz and the other 5.8 gigahertz. So you could make your sensor mesh, those are pretty much all 2.4 gigahertz, and then you could make your backhaul either 900 or 5.8 gigahertz to avoid interference. And again, you'd have or you could have 802.15.4 radios in the pink, and then 802.11 with the blue line. So a lot of different ways that you can make sure that you're managing your traffic in your network, okay, and minimizing the interference within your own facility. Okay, and the other thing that happens with 2.4 gigahertz, we've talked about potential interferences and so forth, is meshing. All of us have heard of mesh. So now if we look here, we've made a mesh network at the backplane, the backhaul, but we could also have the same mesh here at the tank farm. So we have the access point, we have a similar mesh down at the tank farm where all the different field sensors can access that, gain that access point. And so the key to a mesh is that each node has visibility or access to at least two other nodes, right? That's basically the definition of a mesh. So you have a primary and a redundant path to the next node. And then when you put all this together, you can see here we have in the lower left an SP100 sensor interface, and with this we have the 100, and then we have a gateway that connects together. Over on the right, we might have the wire and LPRO WIB network or a wireless HART interfaces coming back in, and then we have our 802.11 network here in the center. And then if we're going longer distances, we might have a WiMAX or a GPRS, right, radios or licensed radios going back to the fixed frequency licensed radios going for the longer distances, say out to a well site if we were tied into a gas plant, or maybe out the longer distance to a tanker coming in and out along a wharf. So we got all this technology and all these measurements we're trying to make, but what does it cost us if we don't know what's going on? Well, as we said, right, the one thing that that affects us is the uncertainty, the quality of the signal. How many times, if you have a traditional analog signal, how many times have you been running on a signal that's bad or failed and you have no way of knowing it because the 4 to 20 signal has been frozen? Well, with a digital signal, whether it's wireless or field bus, certainly with wireless, as soon as you lose that signal, you know it because there's nothing coming in, right? And you get a bad signal. So one of the things you do around uncertainty of signal is you create a margin, a safety margin from your operating limit. So say you had to operate your process at 500 psi. That was the maximum design. So what you would say, well, if I knew everything was perfect, I could run my plant at 490 or 495 psi. But because I have this uncertainty, I'm going to run at 480 psi. Well, those extra 10 to 15 psi equal product. Okay. Unplanned outage, if you can't predict the integrity of your signal, what's the impact of an unplanned outage? So then what you have to do for your unplanned outage is design for a fault. Is that redundancy? So now you're buying extra hardware for redundancy, or you're having to design your equipment equivalent to, that there's additional surge capacity or something like that to give you recovery time. And as we said before, without the connections, there's no control, right? So no connections, no control. Just remember that. That's the primary reason. If you don't have a good, solid foundation, how can you build your control system above that? So what are some of the traditional network management responses, types of things we do? Well, to keep it running, right, we'd have multimeters and so forth on testing the network. We'd have software data capture and analysis tools. And then we'd have security systems, right, to separate the different types of communication. And one of those tools would, on the security side, would be Tofino, which is both a firewall as well as a packet. It does analyze every packet going through, and you can use it as a tool to identify, hey, I didn't realize I was having all this extra traffic on my network, and then figure out the source and eliminate that traffic from your network. Very common diagnostic tool for Ethernet, wired Ethernet, is Wireshark, and it was originally developed in 1998. It is downloadable. One of the wonderful things about this tool is you can see all the different types of packet types here, and at the very bottom you can actually look at individual packets byte by byte to see what information is contained within them. However, with moving to wireless and so forth, we need some additional diagnostic tools. So if you look at a plant, right, we have to have diagnostics at the field level and at the process control level and at the historian and archive and ERP level. Well, we're going to be predominantly concerned here with the field level and the control network level. So one of the things that MTL made, another part of the Cooper company, is they have a product for handheld diagnostics for field level networks. And so the beauty of a handheld diagnostic tool is you can go and plug it in wherever you need it along the network. However, as we know, the chances of something happening while you're connected are pretty slim. So what they've done is they've also developed the same tool as an online version. So it's continually there capturing data and storing it in your control system. Plus it has the traditional contact closure in the event of a fault. Then for HART, right, we have the traditional HART communicator. Not a lot of diagnostics built in there, but the multimeter and ground loop meter that we've shown you before is typically used for HART. In the case of Field Bus, again, the same company, the MTL division of Cooper Crouse-Hinds, sells a Field Bus fault generator that allows you to go in or connect it to the network and generate different types of faults to find the weakest link in your network prior to something actually happening. For Ethernet, right, we just have the standard network meter here. Make sure that you have the proper signal strength, wire pairs are terminated correctly, right? On a Cat5 cable, you got 8 22 gauge wires, so it's pretty easy for something to go wrong there. So this is a quick way to identify if those end-to-end connections are secure. And for fiber, we have an optical time domain reflectometer that serves that same sort of function. For Ethernet tools, these are all, the next few ones here are freeware. They are predominantly designed for the IT environment. Network diagnostic tool is end-to-end test. E2E means end-to-end. Just does some bidirectional testing, makes sure that the messages are connecting from one end to the other of the network. You go to wireless, the most common tool was NetStumbler. NetStumbler has now been replaced with NetSurveyor, of which a graph is shown on the right. The nice thing about NetSurveyor is it also allows you to record and playback. So what you see on that graphic is the use of different bandwidths, different channels within the 802.11 network over time. And then there's another add-in called NetStress that allows you to identify which parts of the network are running closest to their limits. Then there's ComView. ComView is kind of like Wireshark for wireless, right? It allows you to capture packets and search through them, etc., much like Wireshark. Insider is another permutation of NetStumbler, but what it does is it allows you to detect networks. So this is a good tool for doing a site survey, see who's all out there and which channels they're being used and what the intensity of the signal is. Okay. And then Wireless Wizard is a pretty simple tool, almost more for the home network environment, but it just determines how your network's running and the amplitude of which channels, right, and recommends to you the best option. And now I'll hand you back to Brian, who's going to tell you about some tools from Cooper Busman.
Great. Thanks, Ian. Thanks for that background here. And of course, Cooper Busman's been in the wireless business for quite a number of years now. And one of the questions that comes up on a regular basis, of course, is how can I monitor my network? And after hearing these questions over course of several years, we channeled this to our product development group, and they took it on as a product they wanted to develop. And so we asked our user base, what aspects of a software program would you like to have, or what should it be able to do for you? And they gave us some fairly basic things, like they wanted to know when a problem was likely to occur, and they wanted some immediate notification if a problem arose. In other words, if they lose one of their radio links at a particular pump station or something of that sort, they wanted to be alerted as soon as possible. Next, they wanted to be able to build these systems out. We have some customers that have links of just a handful of radios. And of course, that's sort of a traditional method of building things out. You buy one or two and see how they work. And if they work well, then you add to that network. And before long, some of these networks end up to be enormous in size. So they wanted a product that could be expanded and made to monitor literally thousands of data points. And ultimately, at the end of the day, they really wanted something that reduces the operating costs and the expenses and the labors associated with monitoring a network, and of course focused towards a wireless network because of the highly distributed nature and the distances that are involved. Since we have these radio links that are sending communication status like registers between PLCs and 4 to 20 milliamp values, why not use that same radio link to get some diagnostics out of the network? So this is what we began to focus on a couple of years ago when we started on a project to develop a network management system. So this is just showing you some of the other aspects of what customers wanted. Was they wanted something that can interface to their DCS systems or SCADA networks, such that they could deal with some of the information just like they do other process variables like a temperature or flow value, to be able to include things like radial signal strength as just another parameter that's monitored in their SCADA system. They also wanted access over the internet, and of course secure access over the internet. In other words, if they get a page in the middle of the night, it's far more convenient to be able to log on and find out exactly what the nature of the call is or what the nature of the inquiry is, rather than driving out to site to go with a full truckload of tools to find out what the problem is. So they also wanted it to be able to access this over the internet. So, in other words, to be able to scale it with some other equipment available. Okay, these were some of the. This one is just showing you some of the major criteria that our customers had been asking for, and I talk to these customers on a daily basis, and these are a lot of these are, reasonably common sense things that you kind of have to put down on paper before you realize what they all are. And the first is visualizing a network. A picture saves 1,000 words, and that's the objective with visualization, is to have a graphic that shows you the path that these radios are taking, particularly with mesh networking systems, whereby the mesh figures out which repeaters it will use to get data from one location to another. No longer are customers programming specific repeater paths, in other words, manually setting up which repeaters will communicate with which other remote sites. With mesh networks, it's all automatic, and that adds some complexity to the network, which means that we now need a tool to be able to manage that complexity. One of the other factors was historization. Being able to determine the number of comm failures and specifically the times of days that these comm failures are occurring at. Quite often we can correlate that to, well, we had a major windstorm that came through and one of the antennas was loose, began rattling around. The windstorm left, the antenna settled down, and next thing you know, it seemed to work reliably. Or we can sometimes correlate that data to 8 o'clock in the morning, a contractor arrived on site, was using his own radio product. At 4 in the afternoon, he left, and radio comms returned to normal. Or sometimes we can correlate it to things like ice storms that come in, or perhaps temperature-related issues of radios losing electronics and radios losing communications under either extremely high or extremely low temperatures. So that's a very key piece of knowing when, how frequently, and therefore under what conditions comm failures or hardware is being stressed. Then it was security management. There's all kinds of aspects to security of being able to view a network, as well as being able to change some of the wireless or radio parameters, being able to do that remotely. Extremely valuable, but also brings with it some security issues. So we certainly had to make sure that was addressed, and that customers, especially with very large networks, could be comfortable with it. Then we have fault and alarm management. There's a number of different parameters that can be monitored. So customers want to be able to, know which particular parameter went into an alarm condition and this sort of thing here. So these are just giving you an idea as to some of the criteria that we look at when we're developing a product. And again, the overall objective here is to make networks more reliable, reduce downtime, and improve the consistency of the product that these are monitoring here. So going on a little further here, this was some of our product management groups feedback related was they heard that people wanted something web-based. If it came from a platform that people were familiar with, it would certainly have much greater acceptance. Various hardware types, from your typical laptops to smartphones and this sort of thing. They wanted a system that they could access using their own device, whatever they preferred. Then we had to make sure it was agnostic, so that it wasn't focused exclusively on one manufacturer's products. And this was very valuable as well, because this meant that once if you get involved in this software program, that it was not specific. It didn't lock you into one manufacturer's hardware. So we tried to make something that would adapt to any kind of wireless protocols and can also handle hardwired networks as well. So those were certainly some very important aspects. And then they wanted something that was that could be scalable. So if they ended up with a network of over 1,000 devices, that the software program can handle it, that they won't need to go buy something else or upgrade to be able to do so. Currently, we have this network management monitoring a system of over 1,000 wireless links. So certainly have one customer who's seen a significant value in being able to do this. And you can imagine, with 1,000 radios covering a facility, and this particular facility has over 50 buildings. Each building can have several hundred radios. How on earth would you ever troubleshoot a network that large? One of the questions just becomes, where do you begin? Where do you start with a network that large when one link loses communications? And one of the other aspects was to be able to access this information from anywhere. So over the internet, we wanted to make sure that if one user had logged in, that it didn't lock out all other users. So allowing multiple users to access the system is another critical parameter, as well as connecting up to an existing SCADA system. Lots of pulp and paper mills and refineries and water treatment plants, etc., all have a large SCADA system in place. And if this can be integrated with it, such that a handful of parameters for each radio link can now be monitored via as data in a register, just like any other process variable, that would allow them to integrate it, and we would see much greater acceptance. So these are all conversations that we had with ourselves and with our customers when we thought about, where do we go from here? How do we make wireless systems easier to manage? So visualization is one key thing here, and I'm going to just kind of zip over the next couple of slides because they just kind of chat about what we did and what some of the capabilities were, and once we dug into it, what could we do here? But the snapshot in the upper right-hand corner, with mesh networks, that type of snapshot is absolutely key. It shows you which radios are taking which paths, and possibly which radios might be a bottleneck or a critical radio, because they perhaps function as repeaters for multiple remote units. So those particular sites you'd probably want to pay a little more attention to. So then we had requests from customers that said, well, great, that network diagram is fine, but where physically is each of those locations, where are they? And so we integrated it with Google Earth. And this allows you to have an overhead snapshot of your facility or a plant or of a city, and you can now see where each radio is located. So you now know that, oh, that's a radio station. If it's a municipal organization responsible for water, wastewater, you could say, oh, that's a specific pump station. We know exactly what intersection and what corner that's in. And we do have some customers that have mobile networks, whereby the radios are battery powered and they're moved. Monitoring equipment, they're moved from location to location. So this allows you to kind of figure out roughly where the radios are by which other radios they are connecting to. So the picture being 1,000 words, that was certainly a very valuable aspect of this software. And Then we thought about what about automatically discovering it and making the software reasonably smart. So that was another certainly aspect that we built in here. Okay, I'm just going to gloss over the next couple of slides here. They show you some samples of some of the work that we did and what is possible and what's capable in a network management system. This one is just showing you a master location there that's communicating with a number of remote links. The thicker the line, the stronger the signal, and of course the red line that you see in the lower right-hand corner indicates that we have no radio link, that we've lost communications with that remote site. So this helps tell you, especially with mesh networks, exactly which radio links are working well and which ones are not. Okay, then this one here is showing you one of the beta sites that we had set up where we set up some fairly long distance radio links, and this is in just east of San Francisco. And you can see that we've set up some significant long distance radio links here. And when you do so, if you can think about the driving time that's involved, this can be a significant labor saving tool. So especially if we ended up catching rush hour traffic in the Bay Area, this could end up saving hours and hours of time. And if you've got remote access from home, you could log into this system if you got a trouble call, and first thing in the morning, drive directly to a particular problem site with the right tools on hand. Okay. Some of the other aspects are monitoring the performance. In other words, how much throughput are we able to get on particular links? Which are the more congested data points, and possibly how can we resolve that or make changes to the network? So these are showing a number of different capabilities that we added into this system here. Okay, here we go again. It's just showing you a snapshot here of some details of some of the radio links. This is showing an 802.11 radio system that we had set up around our office to test it. And so here we can log in, we can find out IP addresses of different radios, find out what types of devices they are, how well they're running, and the usual green is good, red is bad visual indications here. And here we go. This is showing some more things, incorporating the ping tool into the radio system, and due to the quality of radio links, the level of interference that you have at different times of the day. Some radios only transmit when they have data, so that might indicate that performance results might vary depending on the duty cycle of a source of interference.
But it takes your time.
So a number of different monitoring aspects we have available to figure out exactly how well the system is performing. Yep. Okay, and here we go. Orange, of course, means that we've got something going on. Yellow is just our yellow traffic lights. Things are working okay, but not that well. So this can give you an idea as to how many retries a radio system is doing. And that will give you a very specific indication. If a radio has to do a lot more retries, then clearly it's got some communication problems and it's not performing all that well. Otherwise, all that information is hidden. You have no idea really what the radio is doing in the background, and whether a fault is likely to occur. So some other aspects that we thought about are, I think I emphasized the security aspect. It had to be secure. Otherwise, well, customers just won't use it. And, of course, the bigger the network, the more secure, frankly, it has to be. And one of the things I haven't really chatted about here is exporting data and converting it into Excel spreadsheets and this sort of thing, and making it available as registers so you can read in a DCS system using Modbus, for example. So allowing you to utilize that data in other fashions as well was a key aspect here. And here we go. This is just showing you some account management features to let different users onto the system, set them up with accounts so that they can either just monitor or perhaps monitor and control. And here we go, more graphics indicating the performance of the system, indicating uptime, so that you can see ultimately how reliable are you getting the 5 nines that the customer has requested, the 99.999% reliability, or where does it fall on that scale? So just gives you a tremendous amount of information compared to what was involved previously. And frankly, it's now becoming a requirement with the expanding size of network systems. And I think at this point we pass things over to Ian, and Ian's going to chat about designing a wireless system. So this is a very interesting part of the presentation.
Thanks, Brian. So here's as we say, we said all along, it's only as good as your foundation. And when you're doing a system, obviously the foundation is the design. So one of the things you want to start with is a survey, so you just understand what's out there, right? So you have to do a security survey. So for the security side, right, we're saying it several times, it's commercial technology. We're using 802.11. We're using 2.4 gigahertz that everyone else can use. So you want to do a site survey then to see what's interfering, and like Brian alluded to, some of the things that will change over time. And so you got to do both a security and a site survey at the start, and be aware of who else is using the same frequency, right? I gave the example earlier of differences, right? Using diversity, 15.4 for the sensor network, 802.11 for the backhaul, or 2.4 gigahertz and 5.8, or 2.4 and 900 gigahertz. So these are the types of things you also have to look at when you're at the start of your security issue. So the first thing is, like we said at the very beginning of the presentation, what are your requirements? What's your response time, etc., right? Your data throughput. What are your corporate policies? That's especially true for the security side. Then do your RF, right, your radio survey. How are you going to do your maintenance and support? I think Brian's showing some tools there. And then you have to integrate the two. The policies, right? So what classes of devices can connect to the network? Basically, do we allow, are we an ISA 100 only? Are we going to do ISA 100 plus wireless HART? Are we going to allow Bluetooth? Because Bluetooth is at 802.15.4 and all these types of things. And then create your storyboard of the applications, which basically is create a saying, here's the applications, or these are the things we want to be able to do with our wireless network. So does it mean monitor rotating equipment? Does it mean we're going to actually use it for closed loop control? Just what exactly are you going to do today and in the future? Because remember, you have to plan for the long term. So the first thing is you start with your security survey, right? How much effort do you want to make to compromise your system? I mean, no system is secure, 100% secure, so you want to make sure that yours is harder than everyone else's. Then do an audit, right? Look where's the leakage, so where's the connections, where's the ports, where can people connect, okay? Then do a report on your security audit, and there are companies available to do that sort of auditing. That's just a good place to start would be looking at the membership of ISA 99. And actually the ISA 99 standard is a heck of a good way to look at for ideas of how you should be designing your system to reduce its level of vulnerabilities. Then you move to the site audit, our wireless site audit. So you're going to need layout drawings. where are you going to cover, how much mobility, right? Brian mentioned about mobility, and how much growth, right? So you know what you need to do. Then what competition is out there for your spectrum, right? Is Bluetooth, which is 802.15. What other 802 standards, right? Where else is there power? Like what other places are going to cause noise? Okay, and then we already mentioned moving equipment, different parts of your operation, startup, shutdown, right? That type of thing. What about physical things, right? Buildings, enclosures. I mean, obviously, if you put your radio inside a stainless steel box, that's going to kind of dampen your signal. So make sure you got the antenna outside. What coverage do you have? Okay, how much goes off-site? You don't want to have a lot of signal going outside your facility, even though a lot of the wireless standards have built-in security to prevent being, hijacked. There still is the chance that someone could snoop on you. And then where are you going to put antennas, and what types of antennas? Are they going to be omnidirectional, or are they going to be, just focused in the one direction towards your control room, for example? And then, of course, you always have to write your report and how you're going to implement your wireless system. Okay, so some of the topics in your report are going to be what types of radios, where are they going to be, what ones do you have, and what new ones would you need to put in? Where are you going to put your antennas? What types of enclosures? Are they going to be fiberglass? Are they going to be steel with epoxy coating and antennas outside? Where are you going to get your power? Don't forget to do a site map in 3 dimensions, because radio waves are not in a straight line. If you're going to use antennas, how are you going to get from your device to the antenna running that cable? Where's the power for that coming from? How much data? And don't forget on your 3-dimensional map, your signal strength measurements, and ideally some site photos, right? So you can say, well, this is what it was like when we did the survey, and then as changes come, you could say, well, if we create a model, what is it going to look like after the project, right, if you're doing it as part of a plant expansion. So here's a sort of a survey map, right, where you would do a signal strength reading at each of these eight positions relative to the center. Don't forget, you're also doing these in 3 dimensions. So you're going to do it at at the grade that you're at, and then maybe if you have multiple, if you have, say, a 3-story platform, well, you're going to have to say what's the signal up those the 3 stories of your facility. And don't forget, right, when paths are obstructed, an attenuation, you cannot be calculated, so it's mandatory to simulate or test that capability, right? Mesh does get around that, and that's why it's becoming so predominant in our industry. And just some real simple things to remember is at high frequencies, lower frequencies, right? Remember we said 900 megahertz, 2.4 gigahertz, and 5.8. So the lower frequencies can bounce better and bend, quote, around objects. So they don't scatter as much. It's also inversely proportional to the frequency as the distance you'll get. And so a 900 megahertz will get approximately 3 times the distance of a 2.4 gigahertz type of signal for the same radio. Okay. Look at battery life, how robust, right? That's our mesh type stuff. Check for bit error rates. So basically you have a bit error rate and data rate. So the higher the data rate, the higher the bit error rate is going to be as well. So you may need to slow things down a bit because the more errors you have to retransmit. So whenever you retransmit, you've effectively went and lost bandwidth anyway, right? And for your receivers, keep the distance apart, greater than 2 meters or 6 feet vertically and 10 feet horizontally apart, okay? And if you have 2 antennas running at the same frequency, keep them as far apart as you can on the same tower or the same structure, just like because they're going to have a higher propensity to interfere with each other. So the big thing for your plant, right? Don't panic, right? You got to understand the basics, and the big thing is managing your spectrum, right? Make sure you know who's all using the same bandwidth. So what's the right solution for radio? Well, it's just one of the answers, right? Use something that's using standards. Obviously, are going to help a lot. ISM will help you with expansion. The key thing is manage your spectrum. That means not only your control spectrum, you're going to have to work with the IT people because they're also looking at using some of the spectrum. And make sure that your technology fits their requirements, right? Not just the speed for now and the future. And we've talked about security, right? So two different perspectives, like we said, IT and controls here. We're both using the same spectrum. So industrial automation, the three things we look at are availability, first of all, integrity, and confidentiality. The business land or IT people, they look at confidentiality, integrity, and availability. So corporate people, right, if you get something wrong with your laptop, the first thing they do is they isolate you from the network. Well, if we have a problem with a PLC, that's the last thing we want to do is isolate that device from the network, because now we've lost the ability to control that piece of our process, right? And again, defense in depth, just like with safety systems, the same is true for security, right? Defense in depth means you have personnel controls, that's policy, physical access, right? Who gets into where? Now you're talking into the wireless, right? Network controls, who gets to do what to the network? Then you have containment measures, which we'll show a little bit. So if something happens, remember I talked about the subnets, something happens, how do I constrain it so it only affects the smallest amount of the population possible, okay? And so remember, each one is just as important, just like with SIL, right? You have the whole layers of analysis type thing. The key three are filtering and blocking, which is effectively firewalls and VPN, which is breaking it up, okay? Recovery and backup, so if something happens, you can get back up and running in a hurry. And access control means make sure you have only the right people getting to the right places and addresses, okay? So ISA 99, what they've done is they use something called zones and conduits. So conduits are the connections between the various boxes here. So on the left is a generic zones. So you can see we have different layers of the network. We've got down here operation area 1, operation area 2, and then the control network that notice that the control network, the wireless, is outside that network. We translate that into a plant on the right. You see that there's almost a one-to-one relationship between the two. So then if something happens, right, we would just be able to contain it to, well, let's go here, to just within that one box, right? That's what we mean by containment. So what it comes down to is the bottom line, right, as we said, is increased system reliability at the very beginning. So you get higher throughput, higher product quality as you run closer to your operating limits. Greater measurements at lower cost once you get that infrastructure in place. Workforce mobility or measurements that smaller, less intrusive, new things you couldn't measure before or certainly can measure now for much more economic. And improved health, safety, and environment, for tracking your employees as a audit tracking or of your facility, and then plant security, right? Because you can incorporate boundary security, wireless, gas detectors, etc., for all your employees. And so we'll just let Brian wrap it up here, folks. And there we go, Brian. It's all yours.
Yeah, great. Thanks, Ian. So Cooper manufactures a wide number of different types of wireless products. That's really the wireless business unit. Of course, I guess that's pretty obvious. Wireless is our core strength. We have Omnix control systems in Vancouver, which Cooper acquired several years ago, and They also acquired Elpro Technologies, another wireless manufacturer based in Australia. And by combining those two companies, they've been able to develop some extremely powerful, extremely versatile, and very reliable radio systems. None of these are designed for voice communications. None of these are for our consumer-type applications. They're all for industrial plants. In other words, where your hazardous area certifications are some key aspects, or reliability. And so you'll see us as the manufacturer on a number of major OEMs. We manufacture for a number of different other companies. And we also do a lot of radio remote control of construction site machinery. And this has given us a tremendous amount of experience in the industrial world there. And our network management system, the core, is being used by a number of major companies. And of course, we've designed it to work with a wide range of our products here. So certainly, we're very confident this is going to be an extremely valuable tool for customers going down the road. So finally, just if you have any questions about any of the material on the presentation, this is my contact information. Port Coquitlam, BC is a suburb of Vancouver. So we tell people we're 20 minutes from the U.S. border and 20 minutes from the Pacific Ocean, to give you an idea as to where that's located. And that pretty much wraps things up. So if we have any questions, I think one of the best ways to do it is probably through the online. If anybody would like to type in any questions, Ian and I would be happy to address them.
Well, Brian, looks like they're all still drinking from the fire hose or something here. So